Okay, good afternoon, everyone. Thank you for your coming to my defense presentation. The title of my presentation is Development of Robust Calibration Model for L-oxoic acid Determination in Solution Using Terahertz Spectroscopy. What is the motivation of using terahertz wave in my study? Please look at this. Terahertz wave is new comparing to established regions such as mid-infrared or near-infrared region. And then terahertz wave is located between electronics and photonics region. So it has two special characteristics. It's able to penetrate some non-polar materials such as plastic and paper with low photon energy, so it's safe for biological sensing. Our research group has motivation to bring terahertz spectroscopy into agriculture fields. So one possible application of terahertz spectroscopy is for quality evaluation of juice production. Then please look at this. An IR and mid-infrared spectroscopy has been used for quality evaluation of juice from raw material to juice product before packing. However, so far, no available licensing method that can be used for quality evaluation of juice after packing. Then, why such kind of non-destructive sensing for juice is important to be developed? In the previous study, it has been reported that there is quality degradation of juice product during storage or transportation. For example, L-oxoic acid content in juice product decreased after each week of storage. So, for this reason, it is very important to develop non-destructive base sensing for juice inside packing. However, an IR and mid-infrared wave is difficult to penetrate the packing material. So, it is not easy for quality evaluation of juice after packing. On the other hand, terahertz spectroscopy uses terahertz wave, with able to penetrate some non-polar material such as plastic with low photon energy, so it is safe for biological sensing. So one potential application of terahertz spectroscopy is for quality evaluation of juice after packing. In the previous study, an effort to develop the determination of LA in solution using terahertz spectroscopy has been conducted. For example, Suhandi et al. Has reported the acceptable measurement system for determination of LAA using terahertz spectroscopy. But this system was lacked from the information about the influence of temperature and other components like glucose. So in the present study, I developed the robust calibration model that can be used to compensate these two effects, the temperature and other components. So the overall objective of my study is to investigate the influence of temperature and glucose on the robustness of calibration model for LAA determination using terahertz spectroscopy. But in particular, in this presentation, I'm going to talk about chapter 3 of my thesis because the limitation of presentation time. So I'll focus on the calibration model with temperature compensation. For the first experiment, I used 52 samples of pure LAA solution, and then I measured the spectra of the sample at 3 different temperatures. And then I developed the robust calibration model using implicit and explicit methods. The result of implicit method will explain more detail later. In general, there are two methods for linear temperature variation. First is variable selection, and the second is global calibration. In the present study, I will develop the global calibration model with implicit and explicit method. So the objective of Chapter 3 is to develop robust calibration model for LAA determination, which can compensate the variation of sample temperature using implicit method. For this, 52 samples were used, and then I measured the spectra of the sample at 3 different temperatures. This is the methods of spectral acquisition. First, I will put the sample on the surface of silicon prism, and when the trace wave is come to the silicon prism, some of light will reflect it back into the sample and generate the evanescent wave. This evanescent wave will penetrate the sample with the penetration depth depending on the wavelength. And then the spectra of the sample containing the information will be detected by a detector. This is the parameter used in our study. For developing the local calibration model, 35 samples were used for calibration and validation. And to evaluate the performance of the calibration model, 17 samples were used to evaluate the performance of the local calibration model. Each calibration model was used to predict 17 samples at each temperature. And then, to developing the global calibration model, we combine 2 or 3 different temperatures. For this, we use 70 or 105 samples. And then, to evaluate the performance of the global calibration model, each global calibration model was used to predict 17 samples at each temperature. And this parameter was used to predict to evaluate the performance of the calibration model. The number of PLS factor, coefficient of determination, error of cross-validation, and standard deviation ratio. And these parameters were used to evaluate the performance of the prediction: R-square, error of prediction, bias, SEP, and standard deviation ratio. Result and discussion. This is the typical spectra of LA solution in the triad region, including low and high frequency with same in concentration but different in temperature. And then from here we can see that the spectral differences is larger in high frequency comparing to the low frequency. And then using satisfigulized smoothing spectra, we develop local calibration model at each temperature. And this is the result. From here we can see that all the best local calibration model at each temperature were very good quality with high coefficient of determination and low error both in calibration and validation, and high standard deviation ratio for all local calibration model. Then the performance of the local calibration model were evaluated in prediction step. First, using local calibration at 22 degrees Celsius, we can see that the total error of prediction gradually increasing with the increasing of temperature. And then the local calibration at 22 degrees show us the good prediction for the sample at same temperature. But the prediction was worse for the sample at different temperature. So from here we can see that the effect of temperature difference is larger in terms of bias, not SEP. Then using local calibration model at 31 degrees Celsius, we obtain the good prediction for the sample at same temperature, but worse prediction for the sample at different temperature. And then also the effect of temperature difference is larger in terms of bias, not SEP. And then the same result was observed for the local calibration at 40 degrees Celsius. using calibration at 40 degrees Celsius, we obtain good prediction for the sample at same temperature and worse prediction for the sample at different temperature. Also, the effect of temperature difference is larger in terms of bias, not SEP. And then this graph clearly illustrates the error of prediction in terms of bias. So, for example, using the local calibration model at 22 degrees Celsius, we obtain low bias. And then the bias gradually increasing with the increasing of temperature. So from this, we can see that the local calibration model cannot be used to predict the LAA of solution at different temperature. And then instead of using the local calibration model, we develop the global calibration model. And for this, we combine 2 or 3 different temperatures. And this is the result. The global calibration model were quite good for all combinations with high coefficient of determination and low error for both in calibration and validation and high standard deviation ratio. And then the performance of the global calibration model was evaluated using prediction sample sets. And then this is the result. The prediction result was very good with low error of prediction and high standard deviation ratio for all combinations. So this figure clearly illustrates that using the global calibration model, we can compensate the influence of variation of temperature with low bias. So, using the global calibration model, no bias was observed anymore. And as conclusion, in this study, we investigate the effect of sample temperature on model performance of LAA determination in broad range of terahertz region at 3 different temperatures. And then the prediction result of using global calibration model is improved significantly with low bias in low error of prediction and high standard deviation ratio. And then the last one, the global calibration model can handle the influence of sample temperature on model performance. Okay, that's all my presentation today. Thank you for listening. Any suggestion or comment will highly appreciate it. Thank you.